Okay, so the purpose of this lab is that we want to do a couple of things. The biggest thing is that we want to look at a very simple energy conversion. And we want to look at it from a perspective of the law of conservation of energy, a little bit of work energy theorem, and also efficiency, even though we haven't talked about that yet. Okay, but we kind of generally understand what efficiency is. Okay, efficiency is how much of the initial energy ends up actually being there at the end. Okay, so we're going to be looking at it from kind of those three perspectives, but mostly from the perspective of the law of conservation of energy in a very simple conversion of energy. All right, so the way this lab is going to work, and this is for your design, by the way. Okay, the way this lab is going to work is we're going to have this ramp built. The ramp does not need to be very high. In fact, it can't be very high, or the carts go too far and they hit stuff before they stop on their own. We need the carts to stop on their own. Okay, so don't build a ramp that's like this. Okay, like this thing here with these three books, just to give you an idea, that might be 12 centimeters in height. Okay, that's the book I used. I used 3 of those. Yeah, that might be 12 centimeters. Okay, so it's not very tall, and it doesn't have to be, okay, because we don't want the cart to go too far. Okay, if we build it too tall, it has too much initial energy, and then it has too much kinetic energy, and it takes too long for the friction of the floor to stop the cart. Okay, and that's what we're relying on. So the lab starts with us, as the experimenter, putting energy into the system. We do that by lifting the cart and placing it at the top of the ramp. So I want you to think about what kind of energy the cart will have as a result of you doing work and lifting it and putting it at the top of the ramp. What we want to compare that to is the energy it has at the bottom of the ramp. Okay, so it's going to have a certain kind of energy at the top of the ramp that we as the experimenter give it. Then we want to be able to measure or calculate how much energy it has at the bottom of the ramp. I want you to think about what kind of energy it would have at the bottom of the ramp. We're going to do 3 trials, but they're all the same. We're not changing the ramp, we're not changing the angle, we're not changing the cart, okay? Everything is going to stay the same for all 3 trials, okay? As well as during each trial. You wouldn't like grab the ramp when the cart's halfway down and suddenly make it steeper, okay? So everything is going to kind of stay that way from a procedural perspective. There's also one very important conditional controlled variable that will not change throughout the lab. That has something to do with the planet we live on, okay? And hopefully gravity won't change throughout the lab because it's kind of important, okay? All right, so for our hypothesis, okay, what we're looking for here is we want the if part to basically tell me what does the law of conservation of energy say about this situation. Okay, so the law of conservation of energy, blah, blah, blah. Basically, you're just kind of restating that in your own words, okay? The law of conservation of energy. Okay. The and part will, as always, briefly describe the experiment. Okay? A cart is allowed to run down a ramp, converting potential energy into kinetic loops. Okay. The then part, I need you to predict your results and explain why. There's kind of 2 perspectives you can look at this from. You can look at this from the perspective of the perfect physical world. What does the law of conservation of energy say would happen in the perfect physical world? And you can talk about that in the then part. Okay, and predict your results. You're going to be wrong because this is going to operate in the real world, but that's fine. Okay? Or the other way you can look at it is from the real world. And you can predict what your results will be. How are those 2 energies going to compare? That's what you're predicting. Okay? How's the energy at the top of the ramp going to compare to the energy at the bottom of the ramp? You pick. Real world or perfect physical world. All that's going to change is when you get to the conclusion, one will prove true and the other will not, and you'll have to explain why. Okay? I mean, you have to, if it's proven true, you still have to explain why. Okay? Now, there's a few calculations that we're going to have to do in this lab that you'll only have to do for this lab. Okay, so I don't want you to be looking at some of the formulas that I'm putting in here and going, that's not on my formula sheet, what am I going to do on Thursday? There's some that we just are only using for this lab because it's the way we get the data, so you don't have to worry about 1/2 mv squared, that's obviously important. MGH, that's obviously important. Okay, those ones you would use again. But the stuff about acceleration and the stuff about mass times acceleration times distance, you're never going to use those again in this course. Use them in Physics 20, but not here. Okay, but we need them for today. All right, so what I want to do is first have everybody set up the experiment and get the data. Okay, then I'll go and talk about what you need to do with the data, because otherwise I'll overload you. Okay, and you'll forget stuff in the middle. So the way this is going to set up is as follows. You're going to have one of these ramps, and you're going to have either one of these carts or one of these carts. Okay, these are the better of the two, right? Because they clear the ramp, the end of the ramp better. In this lab, you're letting them go off the end of the ramp. Okay? We didn't let them do that the last time. This time we are. Okay, so they go right off the end of the ramp, and then you got to let them roll to a stop. Okay, and you're going to be recording two things. Once the cart leaves the ramp, you need to start timing it. Okay, so one of the variables that you're going to be recording, okay, and you don't have to put it in your responding variables. Okay, it's just one of the things you're going to be recording. Okay, is how long it takes the cart to stop, but that only starts once it leaves the ramp. Okay, everybody with me on that? So your timer's got to be on the ball. Okay, they've got to be watching that thing, and as soon as its front wheels are off the ramp, start the timer. Okay, and you keep that timer running until the cart stops of its own volition. If it hits something, then you have to do that trial over again. It has to stop on its own. Okay, so you'll be timing it. And once it stops, you're going to mark its position. As long as you mark it the same way every time, you're fine. Okay? But if you measure it differently each trial, that could be a problem. Like, I would say pick the front or the back of the cart as your marking point. Okay? And every trial, mark where the back of the cart is. Okay? Then you're going to measure the distance from the end of the ramp to that point for each trial. So 2 observations you need to have, 3 observations you need to have. Height of your ramp, got to measure that with the ruler. Okay? You can't calculate potential energy without that number. The time it takes the cart to stop once leaving the ramp. The distance traveled by the cart from the ramp to its stopping point. Those are the 3 things you have to record. Now, you only have to measure the height of the ramp once because it's going to be the same every time. Okay? But each trial you have to measure time and distance. Okay, everybody with me there? All right, my suggestion would be that you take a board marker and on each trial, just mark on the floor with a little line and a number. So a line and a 1, a line and a 2, okay, for each trial, and then measure them all at once. Otherwise, you're measuring like the complete distance traveled every single time, and it takes longer. Okay, and I want you to have as much time as possible to work on this in class. Okay, so just mark on the floor and then measure in a straight line as best you can with the meter stick.
Are we going into the atrium for this or what?
No, some of you will be in here and some of you will be in the chem lab. Okay, it's enough room as long as we don't build the ramps too tall.
Okay.
And then yeah, just make sure you have a nice clear path. Okay, some of the trials your cart's going to turn for whatever reason and it's going to smash into something and you'll have to start over again. Okay, but for the most part, it doesn't take more than about 4 or 5 trials to get this done. Okay. Questions on the collection of data? Okay, what are the 3 things we're getting again? Height of the ramp. How many times do you have to measure that?
Once.
Okay. What else? Time from
The
And then the ramp till when it stops.
to when it stops.
And the distance it travels.
Distance it travels, end of the ramp, stopping point, okay? Those are the only three things you need to worry about. All right, so make your ramp, okay? Build it. I think when I did this, yeah, my, I don't remember what my height was now, but it wasn't very high. It was like I said, it was 3 books, okay? So, you know, don't build it taller than that. I think when the ramp was actually on there, it was about 15 centimeters to the top of the ramp, okay? Make sure, obviously, that if you have one of these ones with the meter stick on it, that's the top, okay? If you put that at the bottom, the cart will get hung up on the meter stick. Okay, but we need these meter sticks to stay on here. So if you're using one of the ones that has a stick, okay, just make that the top and measure to here, not to up here, because that's where your cart's.
Where do we put like the height of the ramp? Like in the graph?
No, you're just gonna record it because you just needed to calculate. When we start doing our calculations,
Okay.
you need to do this calculation, which I'll explain when we come back.
Okay.
Okay, I just want you to worry about getting the ramp set up, getting your distances, your times, and your height.
And then for the distance, do we measure from like the end of the ramp to the very end where it stops, or from?
Yes, end of the ramp to where it stops. Okay, and I'll explain why that is when we come back. I just don't want to overload you.
Yeah.
Want to just quickly go over the calculations that you need to do for this lab. Okay, the first one, or the first two, are really straightforward. Okay, all we have to do is get the average distance, the average time. So that's just adding your 4 and dividing by 4. Okay, adding your 4, then dividing by 4. Okay, for your acceleration, we really only need that once. Okay, and so we're going to have it down here. Okay, so we're going to use our average distance and our average time for this, and we calculate our acceleration using the formula they describe on the front, 2d over t squared, right? That's what they have, 2d, yeah, over t squared. Okay, so all you have to do is take your distance, multiply it by 2, whatever your average distance is, and then divide it by the average time squared. Okay, that'll be your number here. All right, so if I was doing that, and I'm just going to use my last 2 numbers here.
And what are we supposed to do for the average for potential energy? It would have been.
You're only going to calculate it once, because it's
Okay.
the same for every
Okay.
trial, right? So I'll get to that calculation here in just a sec. Okay, so I would go like this, 2 times 3.93, okay, get that, and then divide that by whatever the time for that trial was, 9.58 squared, so I divide, not times, divide, by 9.58 squared. Okay. All right, so there would be my average acceleration, 0.085 meters per second squared, and it's negative because it's backwards. Not that that's all that important for what we're doing. Okay, so put that number in here. Now, for your potential energy calculation, that's just m times g times h. Okay, and did I put I think I put in the masses of the carts, did I not? Thought I did. Yeah, here, 0.470. Dynamics carts, 0.470 kilograms.
Is that the same for both cards though?
I will have to find the mass of the silver carts. They're definitely heavier than 0.470 kilograms. So I will test those in just a sec. So if you had the black cart, it's 0.470 kilograms. Okay? All right.
Wait, it's what again? Sorry.
The black, it's on your sheet.
Oh, okay.
Okay, if you had a black cart, it's 0.470. I'll have to take the mass of the silver ones because I don't know what they are. And of course, they didn't conveniently write it on there. That would have been useful. Okay, back to this. And then for your kinetic energy part, okay, calculating the kinetic energy, and this is going to be really important, okay, for not only your calculations, but also for question number 4 in the analysis where you're required to explain something. Okay, here's what happened in the experiment. We can't calculate or measure, the speed of the cart at the end of the ramp. Right? We don't have a radar gun, so we have no way to know how fast the cart was going at the bottom of the ramp. But we need to know its kinetic energy at the bottom of the ramp, which we normally calculate with this formula. Okay, here's our problem. We don't know this number. So what we're going to do instead okay, and this is why we measured the time and the distance, is we're going to say that the change in kinetic energy from the end of the ramp to the point where it stopped, okay, so that's a change in kinetic energy because it goes from whatever the initial is to 0, okay, is going to equal the work done by the force of friction. Because friction is, in the end, what stops the cart. How do we calculate work? Force times distance. Now, this is where the thing is going to be new. We calculate force by multiplying mass by acceleration. That's why we had to calculate the acceleration in the chart. We're going to need it for this. So what we're going to write in here is, yes, the change in kinetic energy, which is going to be our kinetic energy at the bottom of the ramp, okay, is going to equal force times distance, which is going to be written like this. Mass times acceleration times distance, because those are the numbers we have. Okay? So you'll take your mass, which again for the silver cart, we'll find out in just a second, multiply it by the acceleration from here, okay? Multiply it by the distance from here, and that'll get you your kinetic energy at the bottom of the ramp. Okay? Now, you will have to do a little bit of explaining on what I just said, okay, on your own for question number 4. Okay? Because what a lot of people do for the analysis, question number 4, is outline how you determine the potential and kinetic energies of the system, and then they say, I multiplied m times g times h. I know that's what you did mathematically. How did you know to do that? Okay? How did you know that you were using potential energy at the top and kinetic energy at the bottom? How did you figure out the kinetic energy, that whole friction thing I just said? Okay? That's what goes there. Okay? You got to put that kind of in your own words. Right, and then for question number 5, did the potential energy of the system equal the system's kinetic energy? So did the initial equal the final? Why or why not? Suggest reasons for why. Okay? When you're doing that suggestion, I want you to think about all of the things you observed as the cart went down the ramp. Okay? So not just that it went down the ramp. Did it make noise? Did it do any of that other stuff? Okay? Think about other forms of energy that may have been formed as the cart went down the ramp. Okay, so, and 1, 2, and 3, those are just the calculations that we already figured out, okay, or that we already talked about. Okay, everybody with me on that? Okay, then conclusion, same as always, copy paste your hypothesis, explain using your data why you can accept or reject it. So I'm looking for a little bit of stuff on energy and law of conservation of energy in that explanation. And then evaluation. Couple of things to think about in your evaluation would be how you measured, okay? Could there be any sources of error in the measurement? And the path of the cart, okay? I don't think anybody's cart went perfectly straight. Tell me what that means in terms, again, of your measurement of distance, okay? And I'm sorry that the carts don't go straight. There's a couple of reasons for that. They bounce when they come off the end of the ramp, and if the back end bounces and the front end doesn't, which is what usually happens, it turns, okay? The other part of it is the floor is not level. Not even close, okay? Because, yeah, we had some issues with the concrete when the school was built, and there's lots of big bumps, okay? You don't see them as much now because they've put like layers of filler under the floor, but that is the 3rd or 4th floor in the atrium, okay? Because the floor was so wavy that the expansion and contraction caused the floor to pull up because it was so uneven. It was so bumpy. You could actually look down the atrium and see, it looked like you were looking at a picture of the ocean. Okay? There's waves in it. Okay? But they've since filled that in, so it's like half level now. Okay? But yeah, even the floor in here, it's not perfect. Okay? So you got some sources of error there, how to fix it. Okay. Questions?